So the next talk will be by Floris van Doorn, and he will also talk about the HoTT library, but this time in the Lean system.
Yeah, thank you. So I'll try to be quick because we're a bit behind on schedule, but I'll talk about the HoTT library in Lean. So we've already had a talk by Jeremy on Lean, and there will be more talks on Lean next week. So I will go very quickly over what Lean is and focus more on the library. But so Lean is an interactive tier improver, which was announced in 2015, and it's developed by Leo Demura and Microsoft Research. And it's open source and available on GitHub. So there are currently two versions of Lean in use. The newest version, Lean 3, doesn't support homotopy type theory yet, and there are currently no plans to support it, so who knows what's in the future. But so there is a stable version, Lean 2, where we already developed the HoTT library before, and so we are continuing to work in Lean 2 to develop the library there. So some of the features of Lean include that it implements dependent type theory. It's written in C++ and has multi-core support for parallel checking of proofs. There's a very small kernel, and there, to illustrate that, there are multiple independent type checkers just written by PhD students as just a side project. So that's practically possible to just to write your own kernel. The type theory. So there are standard and HoTT instantiations. So we'll talk about the HoTT instantiation. There's a very powerful elaborator in Lean. You can write proofs using terms or using tactic modes. There's a very nice Emacs mode which checks your proofs on the fly, and there's also a browser version which runs in JavaScript. So the kernel implements the following things. It implements a hierarchy of universes indexed over like an external natural numbers, and they are non-cumulative. So if you have a type in some universe, it doesn't automatically also live in a higher universe as opposed to Coq. So that solves some of the problems with Russell universes because you don't have cumulativity. So,
but I'm sorry, but is there a standard function from one to another?
Yeah, there are inductive functions. So inductive types, you can declare them in higher functions than necessary. And so there's a list function which goes from any universe to any higher universe. And you can prove that's an equivalence and everything. Or sorry, you can prove that the list type is equivalent to the original type. So there's universe polymorphism, which we heavily use so that you can define functions in all universes simultaneously. There are dependent products with the usual ADA rules, and there are inductive types. So it's more, it's much smaller than, for example, in Coq and ECTA, because inductive types only generate the induction principles and the constructors and so on. In the computation rules, there's no pattern matching or something like that. And so to give an estimate of the size of the kernel, so there are reference type checkers, which are about 1,500 to 2,000 types. So some things the kernel does not have are things like a termination checker, fixed point operators. There's no pattern matching in the kernel. There are no co-inductive types, no inductive or inductive recursive types, no universe connectivity, and no ADA rule for variables. So the kernel is really, we try to make it lean, yes. Well, for example, the ADA rule for records, I would actually wish we had it, but it's quite easy to work around it. So in addition to the kernel, we add two things to the HoTT library which you also need to trust. So we add the univalence axiom just as an axiom. And then we add higher inductive types, and I think any bits will like our approach very much. Namely, we just postulate the higher inductive types. So we postulate the constructors and the type formers of the two higher inductive types, quotients and truncations, where this is the specification for the quotient. And we also postulate the induction principle, and then we add the computation rule of the induction principle as a kernel extension.
When you say kernel extension, what does that mean?
So the Lean kernel supports like a way that you add new definitional equalities in your and we add two of them for the induction principle for the quotient and the induction principle.
Is that like a rewriting after that?
I think it's very similar to the rewriting of and so yeah, so when I say quotient, this is the type which I mean. It's also called a colimit of a graph, or sometimes typal quotient, where typal is the adjective of type in contrast to set quotient. So you have a type, and you have a family from A to type, and so it's you get points from A, and you get for any if you have if x is related to y, then you get a path from yx to y. So the identity type in the quotient is freely generated by the relation R. And so we don't use any type in type or resizing rules. So the semantics should be quite tractable. Like I think simplicial types and simplicial sets and cubical sets should both model Lean. I think there are still some open issues with that quotients have like large elimination. So this is not a proof or a conjecture.
Can I ask a question? So, and that's an actual piece of syntax in.
No, this is not. This is only the specification. This is not actual syntax.
Oh.
We unfortunately also
You got my hopes up.
Don't have higher inductive types. And what we use in Lean is that we construct from quotients a lot of other higher inductive types. We cannot construct them all, but we can construct a lot of them which are used in practice. So for example, we construct the push out, and then we get also the suspension, smash, join, spheres, and so on. We can construct sequential co-limits. We can construct higher inductive types with two-path constructors, such as the torus and Eilenberg-MacLane spaces. So there's a construction of the propositional truncation, and then Egbert has a construction of all the n truncations, unfortunately not yet formalized. So if this would be formalized, we could even decide to remove n truncations from the kernel and only have quotients, and even more general localizations. These can all be constructed from just quotients. So on top of the kernel, there's an elaborator which figures out all the implicit information. So it figures out implicit universe levels. So you can write universe levels explicitly, but most of the times you don't have to. There's first order unification and higher order unification. It does computational reductions, overloading, coercions, type class inference, definitions by pattern matching, and tactic proofs. So a lot of the features which you want and expect. A theorem and a proof assistant. So this is, for example, some of the pattern matching Lean can do. So it can do dependent pattern matching like this on vectors. So for example, in this example, we define the tail of a vector, and we only have to do one case, and the nil case is automatically discarded. Well, solved by Lean. It's discovered by Lean that is not necessary because you say that the vector is a positive thing.
May I ask a question about this index? So what is the difference between the end of the lines, this and the last line? Like you don't have a period like in code.
Yeah, so there's no period to distinguish when a proof is ended. So a proof ends basically when you write, like, when you have a new definition or something that marks the end of this.
Oh, kind of the beginning of the next one is
Yeah, so if I continue writing on this line, then it would be treated as T applied to whatever is on the next line.
Where will Lean is not like Haskell, is it? I mean, it's not sensitive to two-dimensional layout.
No, it's not sensitive to this.
It's more ML than Haskell.
Oh, and what I should mention here is that all these pattern matching notations are then compiled down to recursive because the kernel only knows recursive. So this is all compiled down to applications of just recursive. So this is another feature of Lean. You can do nice calculational proofs. So this is an example. If you have a type and two families over that type, then the sigma types commute. And there's a nice calculational proof where you write the left hand side is equivalent to this, is equivalent to this, is equivalent to this, and then here are the proofs of why those steps are valid. And then, for example, this is an example tactic proof. I'm not expecting you to read this, but so, for example, this is the dependent universal property of the circle. So this defines just a function if you have so you have a family over the circle, and if you have a point over the base, and you have a dependent path over loop, then you get a function out of the circle. And one nice thing what you can do is, so we do introduce a variable to the circle, and we can use the induction tactic. The induction tactic, we can configure it so that it also works for induction of higher inductive types. And it will recognize by itself if it has to do dependent induction or non-dependent induction. So then the HoTT library, so it's separated into two repositories, the HoTT library, which comes with the Lean 2 itself, and then there's a spectral repository where we are working more like, that's more for the in-progress formalizations, which are still very much changing every day. And then if something is stable in the spectral repository, we move it to the HoTT library itself. So they are sort of there's no big distinction between them. Eventually, we'll probably move most things from the spectral repository to the HoTT library. So the main goal of the HoTT library is to explore and formalize synthetic homotopy theory. There are also some other goals. We've done some category theory. We've done some experimentation with higher inductive types, mostly reducing higher inductive types to quotients. And this is an example. This is the count of the lines of code. So in pure code, it's like 33,000 lines in the HoTT library and 11,000 lines in the spectral repository. And there are many contributors. Jacob van Brouwer, Ulrich, and then a couple of people over here, Jeremy, Egbert, Steve, and Mike has contributed, and many others. I can list all here. So these are some of the things which are of synthetic homotopy which we've formalized in Lean. We formalized almost everything of chapter 8, the synthetic homotopy theory chapter of the HoTT book. So that includes the Ferdital suspension theorem, Whitehead's theorem, the Seibert-van-Kampen theorem, long-stack sequence of homotopy groups, the complex and quaternionic hop federations. We've computed homotopy groups of spheres, and then there are things which are not in the book, like the adjunction between the smash product and pointed maps, cohomology theory, and the Serre spectral sequence, which is almost done. And then there are work in progress about spectra and homology theory. Also,
sorry, for the spectral sequence, you probably need something like CAA complexes.
no, we don't. It works for any type.
Mm.
The Serre spectral, yeah, the Serre spectral sequence works for any type. And so this is a rough estimate the things I've highlighted is a rough estimate of things which are only formalized in Lean, where there should be an asterisk here. So there have been different formalizations of the long sex sequence of homotopy groups, but I think our formalization is the only one where you can get conclusions of the actions of maps on end homotopy groups directly. And then the quaternion and the Hopf federation is only formalized in Lean. I think the computation of pi free of S2 is only formalized in Lean. And then the smash pointed maps adjunction and the search fractal sequence are also not anywhere else. So this is the long sex sequence, the statement of the long sex sequence of homotopy groups. So if you have a pointed map from X to Y, so that's a map which preserves the base point of X. So it sends the base point of X to the base point of Y. And then you get a long exact sequence of homotopy groups of this, which relates the homotopy groups of the space of Y, the space of X, and the space of the fiber of F. And then you also have the horizontal maps. You can compute exactly what they are, and diagonal maps are given in the proof.
I have vibration sequences quite advanced in foundation. From where it doesn't seem to be very far to here.
My experience was that the translation, so getting from vibration sequences to here is actually the largest part of the work. That is my experience in formalizing this proof.
And vibration sequences give you the periodicity.
Yeah,
I mean, it
so
gives
the
you
vibration sequences gives you this sequence, but then you have to prove that it's actually equivalent to that sequence, and that is actually quite challenging, and that the maps are correct also.
Well, that's probably equivalent to describing what are the maps in the derived vibration sequences between the spaces themselves, which is something which is in my treatment. But okay.
So this is another example. So this is work by Egbert and Ulrich, formalized by Ulrich, which about the Hopf federation. So it assumes that you have a type, an H space on A, and then A is path connected, and then you can define a Hopf map from the suspension of A, a family over the suspension of A, and then the total space of that is a join of A with itself, and then there's an H-space structure on the circle, which gives you the complex Hopf federation, and an H-space structure on the free sphere, which gives you the quaternionic Hopf federation. So here's the statement of the adjunction between the smash and the pointed maps. So it says that this PP map is the pointed type of pointed maps from between two types. So it says that pointed maps from the smash product to any other type is equivalent in a pointed way to pointed maps from B to pointed maps from A to C. I could have swapped the A and the B. This is the statement, and from that you can, for example, derive the associativity of the smash and the naturality of that associativity. This equivalent is also natural, which is not shown on this slide. We did. Let me skip the item, this about eigenmark plane spaces. So this is the statement of the search spectral sequence. So here is a statement in words, and this is a slightly more general way how we formalized it. So the search spectral sequence says that if you have a simply connected pointed type X with basement X naught and a family over X and a group G, then then there's this arrow, and then there's a group here which is the cohomology group of the total space of F with coefficients in G. I don't want to go into the exact definition of cohomology group, but it's some algebraic property of any space. This is the cohomology group of X with coefficients in another cohomology group, namely the cohomology group of the fiber in G. And this arrow means that in some technical way, this type, or this should be sigma, the total space of F is Z, so that this cohomology group is in some technical way built up from these cohomology groups. And this is the statement in Lean, which is a parameterized version of that. So I want to do one small extra on pointed maps. This is like a design, more design, how to design a library than about the hot library, specific to the hot library. But so a pointed map from A to B is just a map which respects the base point. If you build enough libraries, enough of the library, you will realize that at some point you will need to generalize this to dependent pointed maps. So a point dependent map is a dependent map which respects the base point. And actually here in this formulation you notice that you don't assume that B is a pointed type everywhere, only over the base point A. So you can even generalize this slightly further to say that you have a pointed type and just a type family over it and only a point in the base point. And then you can define a dependent pointed map, like a pointed map which shares the base point like this. And so what this gives you is, well, that you can define these two as special cases of this. And one thing this gives you is that you can define a pointed homotopy between two pointed maps. So if you have two pointed maps F and G, which can be either of those, so let's say this because that's the most general, that is an element of a dependent, so it's a dependent pointed map from A to equality, so from equalities from FA to GA. Because you this makes sense because we have a base point over the fiber, namely there's a point in here which is just a concatenation of the facts that F and G respect the base point. And this is very nice. For example, you can define two homotopies, so a homotopy between homotopies as just again a pointed homotopy. So this is kind of an engineering solution to reduce the amount of different concepts in pointed type. You only need pointed dependent maps, basically. As a conclusion, so some of the I will, as a conclusion, list some of the advantages and disadvantages of Lean. So Lean has very powerful unification, which allows you to make higher order arguments implicit. So when you have a transport or dependent path, you most of the time don't have to write the family over which you transport. It has a very small kernel, and it has a large library for synthetic homotopy theory, and it's also very fast because it's it's written in C++ and has multi-core support, and there's a lot of effort done in the performance. So the type checking is quick. So some of the disadvantages is that, powerful unification actually also has a problem, namely when you write a term which is type incorrect, then the Lean elaborator will look through all kinds of possibilities to figure out what you mean, and then at some point it will know that all the possibilities failed, and then it will give you an error message which sometimes does not have anything to do with the place where the actual error is. So that's kind of annoying. So the powerful unification degrades the error messages. There's no active development to the source code because we're working in the Lean 2 branch. And one problem is that so to simplify the goal, just to show the goal in a convenient way is sometimes hard to do. So it would be nice to have better tools for that. Thanks for your attention.
Thank you.
So on your last slide of the disadvantages,
Yeah.
at least the first two, it seems, are ones which would both be solved by upgrading to Lean 3, except in
Yes.
principle. Would the third one also?
Yeah, I think so. So Lean 3 has a lot of tools to support your own automation and so on. So you can write like a definitional reducer which just does some definitional reduction to your goal, and then to simplify your goal. And I think since you have a lot of control over what it does, I think that would solve the third problem as well.
And what is the problem to put in library to link 3?
Nobody has offered to do it.
I mean, there's
I'm
no
not
hot support
able.
in Lean 3 itself.
Yeah, so there's no hot support in Lean 3.
Why is that?
So the developer is under a lot of pressure to just deliver a product for the standard modes for program verification and things like in at Microsoft Research, and he didn't have time to maintain also hot support.
Also, I mean, one reason he also cited is that it's apparently not so clear what you actually want to have in hot, as far as I understand. So, should he directly implement cubicle hot already, or is it, should he go first with usual hot and later? Is it required to extend it?
Yeah, one of his arguments is also he doesn't want to spend effort to support hot, so to just support like the hot in the way it's done in the book, because his argument is that what we homotopy detectors really want is a cubicle system with, and so he doesn't want to spend effort in a system which is not optimal.
So how long would it take to actually implement cubicle in?
I think you should ask people who have experience.
I mean, there's an implementation in Akka now, so.
I have no idea.
I don't know, yeah. I think just changing the kernel and maybe elaborator might be feasible, but then there are a lot of things to help the automation and so on top of it, which might be hard.
That was very cool.
Yeah, and one other question. I asked done this already yesterday. So these things like spectral sequence and so forth, they, if I understand correctly, were originally developed to solve problems in number theory, maybe, or maybe also analysis. So anyway, my question would be whether it would be possible to sort of instantiate the synthetic homotopy theory with those, you know, example instances for which these concepts have originally been used, and then maybe get new or more modular proofs of classical results.
So I do not know of applications of spectral sequence to number theory, but they are very powerful too in homotopy theory to, for example, compute homotopy groups of spheres or give properties.
And then those.
Yeah, so we are, if we finish the construction, then we really want to work on applications.
Last quick question.
Well, I have a last question to Peter. How far is how close we are to having a model of the entire inductive type of the scale?
That I don't know. I don't know how the Lean one does it.
No, I'm not asking about how Lean does it. I'm asking whether you can model it in some.
So just the quotient higher inductive type.
Lean
Yeah.
just has homotopy push-ups.
So-
It's just homotopy push-ups.
Right.
So in so what Mike Schulz and my semantics gives in suitable model categories, which in particular includes special sets, it gives that construction, but there's a size blow up, so the universe isn't closed under it with that approach. So you have that construction sort of globally, given two types you have thing, but it lives in a larger universe than they did. There is a trick that Andrew Swan has suggested, which I think might well be able to solve the size blow, but that hasn't been worked out carefully. So I think that's where it stands. It's done with a size blow, hopeful that it can be adapted by ideas of Andrew Swan to get a universe closed under it.
What about in the cubicle sets? That supports
So I think-
some hits, isn't it?
Yep. So there, I think I'm not the person to answer on that, but there I think it's actually a bit less problematic because the primary placement can be taken in a more uniform way. Is there someone here who is a cubicle person and can answer that?
Or maybe we can postpone the answer.
Yes.
And thank Floris again.
Okay.